Hello, welcome back to Math with Patrick. Today is February 13th. We're solving problem number 44. Let's try it out. Looks like we are just simplifying some stuff here. And apparently when you add all of these square numbers together and add all of these natural numbers together, you get 13. Well, it'll be pretty easy to just list out all the numbers and add them up. But I want to see if I can do it in a slightly, let's do it in two ways. Okay, the first way to do it is let's just look at the problem as is. It says that we have the sum of squares from 1 to 6, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. That's what those ... dots mean here. It just means like continue this pattern in the most predictable way you can, and it looks like we're just counting up by ones. And then I'm subtracting all the numbers from 1 through 12. So I'm subtracting this sum. So I guess technically what I should do is add up all those numbers and then subtract that number at the very, very end. So I'll go minus, and then just to kind of honor the problem as is, let me write out the whole sum. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12. Now that I can see all my numbers, let's just square all the numbers that need squaring. So we got 1, 4, 9, 16, 25, and 36. We're adding up all of those. And then maybe I'll add up all these too. And the way that you're supposed to do addition is just left to right. So let's see if I can keep a tally. Let's see, 1, 2, 3, 6, 10, 15, 21, 28, 36, 45, 55, 66, 76, 77, 78. Okay, there it is. I added up all those numbers left to right. And then finally, I should probably add up all these numbers left to right as well. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, 55, then 85, 91. So I have a 91 minus 78. And when you are doing a problem with addition and subtraction, you should do everything left to right. So at this point, I have done all of these things left to right. And so it is appropriate to add up all these first before doing the subtraction, only because the subtraction came very, very last. And then finally, let's see, what's the best way to prove that 91 minus 78 is 13? Well, how about let's count up. You could count up by 2, then you'd hit 80. Then you could count up by a 10. That way you would hit 90. And then you can count up one more time to hit 91. So altogether, I can tell that this is a 13. And there we go. I mean, I'm done. That's the whole problem. All I had to do was some arithmetic. Though I also want to show you a second way to solve this. It would have been pretty tedious to sum up all of these numbers if there was like more than 12. Like if there are 20 numbers, I don't know if I'd really want to go one by one, just adding them all up, trying to count in my head. So there is a slightly faster way to do this. There's actually this ancient story of a teacher who decided to have their students just be busy. And they said, yeah, just add up all the numbers from 1 all the way to 100. And one of the students is a famous mathematician whose name is escaping me right now. But he was able to come up with the sum very, very quickly by adding these numbers with a specific strategy. And that strategy here I can show you with the 1 through 12. If you look at the low and the high numbers here, and you keep making these pairs, they're always going to make, in this case, a 13. 1 plus 12 is 13, 2 plus 11 is 13, 3 plus 10 is 13. And let's see, I have 1, 2, 3, 4, 5, 6 13s. And so for this problem, I could add 13 to itself 6 times, or a slightly faster way to do it would be 13 times 6. Now, this is generalizable. What I'm doing here essentially is taking, well, let's see, 13 times 6. How could I express that just in terms of this 12? Well, one way to think about it, I could see that, well, 13 is just 1 more than this 12, and that makes sense because I went down all the way to here and found the 1 and added it. So no matter what the highest number is, it's always going to be 1 more than it will be in my product. And then for this 12, you can kind of see that I'm grabbing 2 numbers each time. So every time I get a sum, I'm crossing off, well, 2 numbers. And since there's 12 of them, it's going to take 6 steps until I get rid of all of them. That was 1, 2, 3, 4, 5, and then 6. And I'm essentially just counting up half of this list and stopping because I've already counted it on the other side as well. So this 6 comes from n divided by 2 because it's half the length of my list. This also works for odd numbers. Maybe that's something you can prove to yourself too. But this formula will work for any value of n when you're adding up the natural numbers up until that n. The proof for the sum of squares is a little bit harder. There's actually a really good visual proof that, if I remember, I'll put in the description below. And that formula is a little bit more unwieldy. Let's see if I can remember it. It's n times n plus 1 times 2n plus 1 over 6. And so you can use this formula when you're adding up all the squares from 1 to n. Now, for this one, n was 6, and for this one, n was 12. So if I just plug in the 12 and the 6, I'll get 13 times 6, which is, let's see, that's 60 plus 18, so 78 for here. Plugging in a 6 here, I get 6 times 7 times 13 divided by 6. It's convenient that the 6's cancel. And then, 7 times 13 is just going to be 1 more 13 than this one. And actually, now knowing that I'm doing 1 minus the other, I don't even need to know what this number is. I know that the difference between these is already going to be 13. But I mean, it is 91, and the difference between them is 13, which we already established. But I also wanted to offer this other way to solve this problem in case, you wanted to know how to add up a whole bunch of square numbers that, and if the sum was bigger than 6 addends, it would be really convenient to have this formula instead of adding up all those things one by one. So 2 ways. Hope you enjoyed. That's all from me today. Oh, I can't forget. I'm waking him up from a nap for this, but there he is. Say bye, Quilly. Okay. See ya.